Recording started. Thank you very much. And let me share the screen now. Okay. Okay, good. You should see my screen now. Okay, let me get also the chat. Just to make sure that if you write something, I can see you. I'm not very quick in reading the chat, so if you write something and you realize that I don't reply to you, please step in with the micro. Would be also more interesting, so I can hear your voice, which is always nice. Okay, first of all, we are today, let's see the calendar, we are today at April 4th. So we are about midway from the beginning of our joint experience. Be careful of the timeline because as you will see, there are some gaps. And in particular, I am teaching next week, but then there is a break from April 11, which is next Thursday, to April 22nd. So there is 1 week free because I have to attend a conference abroad. And then from April 22, we jump to April 29, okay? And then May 2nd, and be careful because in May, as you will see, there are no more online lectures. The last 3 lectures are in physical presence. And the reason is that we have a limited number of online hours of teaching. And so end of April, we get to the end of our allotted online time. So just be careful of the calendar because it's not as regular as it was before in April, okay? Good. I think I got a question from, not from you, but from other students regarding the subscription to the exam. The exams are not yet published on Alma Esami. And you see here the exam dates. You will find the dates in Alma Esami, I would say beginning of May, and subscriptions will be opened beginning of May. So don't be concerned if you don't see the exams in Alma Esami so far, because it's too early. And in any case, I don't want to open the subscriptions too early, and be patient because I think you also need time to get organized. You have the dates here, and there will be another date in September. I will put the September date as soon as possible. Okay, so you have 4 exams up to September, and then you will have another one in January and another one in February. Okay, very good. Any question related to this? Can I start? Good. So we got last time to discuss the link to sustainable management of water resources. So let me just click here. And you may remember that we got to this point here while discussing seasonality, okay? Now, we started discussing water resources because, as I said, water resources are one of the keys to climate change adaptation. Climate change impact on society takes place through water resources, through other let's say, socioeconomic sectors, which may be, for instance, transportation, which may be other things. But water resources are a key element, because for obvious reasons, because water is necessary for life, because we all understand the importance of water also for socioeconomic development, the importance of water for producing food and for supporting the industrial production, whatever. And also we recognize the role of water for producing energy, and in particular through hydropower. We said that water resources play a fundamental role because through hydropower generation, we not only get clean and renewable energy, but there is also the possibility to store energy, because by storing water at high elevations, we, in a way, store energy. And there is also the possibility to use the energy produced by other renewable sources. There is the possibility to store energy produced by renewable sources like solar electricity or wind power, they cannot be stored by themselves, but we can use water as a battery, because when we have an excess of solar power, when we have an excess of wind power, we can use this excess of energy to pump back water from downstream to upstream, and this is actually what we do. I think I already mentioned to you this possible solution, and in this case we can use water as a battery, because we give the excess energy to water in terms of potential energy. We bring water upstream. We store the water in the reservoirs, and we can use hydropower, the energy that we stored, to compensate the periods in which the other renewable sources are not available, like during the night for the solar energy, or period of without wind for the wind power generation. So water resources play a fundamental role, and therefore the impact of climate change on water resources is important, is concerning, is in a way interesting to study. This is why we discussed the climatic zones, we discussed the seasonality, we discussed the distribution of water resources, because as I said, we have plenty of water, fortunately, in the Earth system. Water is conserved. On the other hand, the distribution in time and space is uneven, as I said. And therefore, we have this problem to solve: how to compensate for water resources variability. And then I said, to compensate variability in time, we can use artificial reservoirs. And I ended the last lecture by discussing the importance of dams and also the downsides of dams. And then I said that to compensate for uneven spatial distribution, we can use the virtual water trade. We can export, we can trade goods whose production requires a lot of water resources. And then through these solutions, we can compensate the uneven distribution of water. And these solutions, the virtual water trade and the artificial reservoirs, are examples of strategies for climate change adaptation. I want to give you the example of the Po River. In the Po River, we noticed recently, after global warming, that the river flow in spring is increased. I already discussed with you this. And conversely, in summer, we have a decreased river flow because of the anticipated snowmelt. So the total amount of water that flows in the Po River in a year doesn't change. But the distribution changes, the seasonality. This is why I keep this figure over the screen. We have more water in April, less water during summer. How can we compensate it? How can we adapt to this change? By storing water. And artificial reservoirs are a possible means to adapt. So these are first examples of solutions. And I think it is extremely interesting to discuss climate change adaptation strategies with respect to water resources, because I think they are really relevant on the one hand and instructive on the other end, because they are solutions that whose meaning, whose underlying concept can be easily understood. Storage, for instance, storing water when it's in excess in order to have water available during periods of scarcity. So these are, I think the concept is extremely educational because they can be easily understood. So this is why we are discussing sustainable management of water resources, where sustainable means that in front of climate change, we find solutions to adapt. Today, I want to discuss with you other possible solutions for climate change adaptation with respect to water resources. And this is the remaining part of this lecture. If you scroll down, you see here other possible solutions. Let me take the PowerPoint, and meanwhile, while I take the PowerPoint, do you have any question so far? Okay, let's go to the right slide. Here it is. Okay, so another possible solution. I mean, these are examples that I want to give to you. I am not exhaustive, okay? So there are other possible solutions, which I can mention briefly. On the other hand, I want to discuss with some more detail the solutions in terms of water resources management in front of climate change that are more frequently applied. So increasing water supply is precisely the realization of reservoirs. It means finding more water. So, you know, already the Romans, when they had to cope with increasing water demand, they used very long and very complex networks of aqueducts to move water hundreds of miles from areas of abundance to bring water to Rome or to other cities. And keep in mind, they didn't use pipes. They use open channels to bring water to the cities. So the result is these fabulous architectural remains, the Roman aqueducts, which are really an example of early, not very early, but an example of engineering already 2000 and more than that years ago. So basically, there are other examples. And for instance, the reservoirs that we realized over the Po River Basin, there are a lot of them. And the reservoirs that we realized in Italy, all over Italy, in order to precisely increase the supply. So more water not in absolute term, because when we build a reservoir, we don't find an additional volume of water. We just compensate the distribution in time. Other solutions are, for instance, the use of groundwater, which means that if I don't have enough surface water sources, I start using a groundwater. And this is another solution to increase water supply. I mean, there are several other examples at the international level. And you know that currently in Asia, construction of reservoirs is still ongoing with the realization of very huge dams. It is interesting, if you go on a web page, it is interesting to search in Google the list of big dams. And I think there is a Wikipedia page here, list of largest dams. Okay, and you see here a list of the largest dams in the world, and the reservoir volume is particularly interesting. It's not ordered here. You can order in terms of reservoir volumes, and so the biggest so far that we have is the Aswan Dam, and then the Guri Dam, Three Gorges, which is quite recent. The Three Gorges, if you look at the year completed, is 2008. And if you order for the year completed, first of all, let's start from the beginning. From the beginning, you see that we start from 1932 with the big dams. Of course, we started earlier with smaller dams, but for the big ones, and this is a dam with a capacity of 5.5 billions, so it's indeed quite huge. And to give you an idea, the Vajont Dam in Italy is 1/4 billion. So you understand that these are really big. And so we start from 1932. If we go to the recent ones, in this list, the last one that we find is the Three Gorges. Here you can't see the Millennium Dam, which is under construction in Ethiopia. And I don't think is larger than the Three Gorges. You can check, Google, Millennium Dam. Millennium Millennium Dam. Here it is, and there is a Wikipedia page. Oh, this is in Italian, sorry for it. And let's say here English. Let's see if it works in this way. No, and let me go back. Okay, I think, let's see. Let me go back to find it in English. And here it is. No, this is a video of the producer. Here it is. Okay, and the capacity is, let's see, location, coordinates, dams in pound, no, height, length, dam volume. It's 10 billions. 10 billions. So if I go back to the previous list of the largest dam, here we are in capacity, we are 39 billions. So maybe that the Millennium Dam is somewhere here. It's not ordered in capacity. Okay. Anyway, I was looking for the recent ones. So you see the last one that is listed here is the Three Gorges Dam, 2008. Another one in India, 2005. Another one in the Philippines, 2003. And then Turkey, Tajikistan, Austria. So you see that if we look at the largest dams, there is quite relevant activity in terms of construction in Asia. And the reason why the most recent dams are located in Asia is that in Asia, we didn't have the opportunity in the past to manage resources, enough resources, and to find the ideal conditions to build these huge dams. In the Western world, the conditions were found some time ago. Before than in Asia, and this is why in terms of dam constructions in Europe we don't have many opportunities left, while in Asia there are still several opportunities. Okay, so let's go back to our lecture. Here it's sorry, here PowerPoint. Here we are. Okay, so increasing water supply is a possible solution. Okay, and keep in mind that when we build a reservoir, usually we try to optimize the use of it in order to benefit from several different sides. So one side is water resources availability, another side is energy production, another side is flood risk mitigation, because of course, a reservoir is a potential storage, and therefore when a flood comes, if you have capacity in the reservoir to store part of the flood, we can decrease the river flow downstream. So we say that today we try to realize multiple purposes reservoirs in order to profit from them from different sides. It is not always easy because you have different requirements in terms of organizing the storage. If we want to give a priority to hydropower generation rather than, for instance, to water use for irrigation. So it's the priorities are different, and this means that if you optimize a reservoir for hydropower production, maybe that it's not optimized for agricultural production. So management of reservoir is a science in itself. If you look in the literature, there is a very extended literature starting from, I would say, from very ancient times, but in particular with a lot of activities in the past 30 years on optimization of reservoir usage. And it is a very actual field because when we got the availability of modern computational resources, we could study the management of reservoirs on the basis of automatic procedures of optimization. So optimization theory has been a pillar of water resources management recently. we don't focus on it, but at the end of the course, I will dedicate some time to decision theory, and a part of decision theory is regarding precisely the optimization of reservoirs. Okay, so increasing water supply, what is the downside of it? There are downsides. Keep in mind, when you find a solution to a technical problem, a technical solution to a problem, you always have downsides. And because, of course, at least you have the cost of it. At least you have the environmental impact of it. So any solution is a modification of the natural environment. And you have always to consider cost and benefit. And in fact, very often we use decision theory to find the best solution. You will see that today we are discussing different solutions for optimizing water resources management, and some of them are in alternative. And this is why we will discuss decision theory. Decision theory is not a fascinating topic by itself. It helps us taking decisions. It's not really fascinating in itself, but if you think the potential applications, it becomes really interesting. It's like probability. It's not fascinating in itself, but when you see the potential of it, decision theory is really wonderful, the potential of it, because it really helps you. This is why we will discuss something. So in terms of downsides, what is the downside? What are the downsides of increasing water supply? First of all, the cost. And I think this is an interesting slide because it is a bit old. It's I think 10 years old. So maybe that in the past 10 years, in the recent years, there has been some changes of it in terms of, for instance, the cost of energy. So you see that here, first of all, what is really clear from this picture is the cost of desalination. Desalination is, of course, an interesting opportunity, but it is very costly. It requires a lot of energy at present, and there is the problem of the displacement of the residuals of the salt. Because it's not salt that you can use for selling it, for using it in producing food. Unfortunately, is contaminated salt. So displacing this material, the residual from desalination is a problem, and this also explains the costs. And there are the costs of energy. Keep in mind that currently the desalination plants work through evaporation and distillation, basically. And this is why, or let's say distillation is not a proper term, evaporation. And this evaporation and condensation. And this is why it requires a lot of energy. Now, there is a lot of research activity in chemical engineering to study the potential of filtration through membranes in order to remove the salt from water. Indeed, it is much more energy saving. It is less expensive in terms of energy. It's still limited in applicability because we can't get a huge water volume by filtration. It is a bit slow, the process, and this is the current limitation. But for sure, in the future, filtration will become more affordable, and it may represent a great solution with, of course, the problem of the displacement of the residuals, of the resulting material. And you understand what is the potential of desalination, because 97% we discussed of water in the Earth system is salted water. You see here that the cost of desalination at the global level is represented by quite a tall bar. The height of the bar represents variability because on the vertical axis you have the cost. And so at the global level, of course, the costs are different because the displacement of the residuals may be more costly in some countries. For instance, in Italy, we don't have room for it, so it is very costly, and we may need to export it. And in other countries is cheaper, and also the cost of energy in some countries is cheaper. And this is why you have a variability of the cost, but still the cost is very high. It's definitely the highest. And then also the treated wastewater is quite costly. This is an opportunity. In some countries, they already use the treated wastewater for civil use to get potable water. Okay, drinking water, sorry, this is more correct term. And drinking water can be, in some countries, is derived from wastewater treatment. And also in Italy, we get drink water from rivers that originally are quite polluted. For instance, in Florence, the water supply takes water from the Arno River. And it is a river that it's affected by pollution. It's not very polluted, it's not wastewater, but still it needs quite an extensive treatment. So basically, wastewater is an opportunity for sure. And for instance, there have been already some experiments of autonomous buildings that don't need water. They recycle everything. And so they get drinking water and through full recycling. And this is amazing if you think of it. Already in Italy, we use treated wastewater for irrigation, and you can't use it everywhere, but for some zones, for some cultivations, we can use indeed the treated wastewater. Problem is the cost and the volume. Really, you can't solve huge water problems, relevant water problems through treated wastewater. So sometimes it is mentioned as a potentially viable and final solution. Actually, it's not final because the volume it's limited and the cost is still quite important. So this is why in some countries we don't push too much for it because it's really costly. And then you see surface water. Surface water here, it's represented with a quite relevant cost. Actually, it is quite relevant here because it refers to Southern California. And the cost is quite relevant because of the use of dams, artificial reservoir, extensive use of dams in California. The Colorado River, it's not delivering any more water to the Pacific Ocean because they are using all the water for water supply and through the use of several artificial reservoirs. So if you consider the cost of the artificial reservoir, you see that the surface water becomes quite costly. But actually, when you can use the surface water directly without need for storage, it is very cheap. You understand why? It is readily available, and you don't need to pump it too much because it's at the ground level. So maybe that you have to pump it at the highest floor in the buildings, but it's few meters only. So the cost of pumping is not very relevant. It's not like groundwater. Groundwater, if it is very deep, there is a relevant cost for pumping. So surface water usually is the cheapest one. For instance, in countries with a good coverage of mountain regions like Italy, whose surface in Italy is basically it's mountainous. We have only a few flat areas, which means that the surface water is high in level and can flow directly into the houses. So there is no comparison in costs. The surface water in Italy is definitely the less costly with respect to groundwater, with respect to wastewater treatment, etc. So here the situation is not really representative of the global level. Surface water normally is the cheapest. And then there is conventional water treatment is including all the sources that come after treatment, and this is a USA average. And brackish water is surface water that is stored in marshes, in maybe partly salted, and in California it is quite cheap to use it. In general, it's in Europe it's not very convenient. And then there is groundwater. Groundwater normally is quite costly. It depends on the depth of the water table, because the cost is related to energy. I can tell you that in Italy, if you talk to farmers, they prefer not to use groundwater because it's too costly to them. So sometimes during summer, they prefer to stop irrigation and lose the agricultural production, the crop production, rather than using groundwater that is for them not very convenient. Okay, so these are the problems related to cost. One second, there is a student in the lobby. Okay, now another possible solution: water demand control and regulation. So basically, increasing water supply is a solution. And what is another downside of increasing water supply is the environmental impact, because you take water from environment. Think of groundwater. The environmental impact is very relevant because, as I already mentioned to you, it may be that groundwater bodies get depleted in the future if we continue to extensively use groundwater as we are doing. So it is something that, I mean, environmental impact is also relevant in terms of sustainability of water usage. So an alternative solution is, instead of increasing the supply, an alternative solution is decreasing the demand. And how can we decrease the demand? First of all, let's keep in mind that water demands are increasing. In general, per capita, they are increasing. You know that in some countries, the population is decreasing. And therefore, for instance, in some regions of Italy, the water demands are decreasing because of the decrease of population. On the other hand, the water demand per capita is increasing, is an indicator of welfare. I mean, when people use more water, it means that welfare is improving. Think of 100 years ago, the water demands were like 1/3 of the water demand for civil use that we have today. In some regions, even less than that. In some regions, 100 years ago, people didn't have the water tap in the houses. And in most of the regions in Italy, people didn't have the water tap, and they were used the portable tanks in order to bring water into the houses. So for sure, you can reduce your demand. There is to say, however, that water demand is an indicator of welfare, but there is some, let's say, degree of freedom in what I'm saying, in the sense that if you increase your water demand for actual usage of water, it is an indicator of welfare. If you increase the water demand because it's not actual usage, but is rather water that is wasted, that is increasing, then this is providing an option for reducing water demand without compromising the welfare. This is the solution that we have to seek. Is it possible, by keeping our trend in welfare increase, our target of welfare increase, it's possible to reduce the water demand without compromising this target? So this is a relevant branch of science in water resources management, reducing individual water demands without compromising the socioeconomic development, because sustainability means sustainable development. So we have to ensure sustainability without compromising the development. Is it possible? Yes, for sure it's possible. And we know that we are being educated to save water. And but how to be effective in educating people? First of all, there is a component that is not dependent on people, or let's say not directly dependent from people, which is water loss. We have to decrease water losses. And it's decreasing water losses means that you have to reduce leakage during transportation, during the leakage in aqueducts, in water supply systems. Keep in mind that in irrigation, it is usual practice when you move water through open channels, it is usual practice to assume that water losses are 50% of the withdrawal. So it means that if you take from the river or from groundwater, 1 cubic meter of water, at the end of the story, you deliver to the field half cubic meter. Of course, it depends this percentage on the length of the channel. It depends on the structure of the water supply system. But even with pipe flow, aqueducts in Italy, even those that are based on pipe flow, they basically experience losses that are around 30%. And this is not only a problem of Italy. It's a percentage that is at the global level, more or less. It's like that. So you understand that it's a lot. It's a lot. If you think of 30%, 50%, it's a lot of water that it's lost. Of course, it's not really lost because water is conserved. So if you have leakages, this water comes back to the environment, goes back to the environment. And some people say that it's good that open channels are subjected to water losses for infiltration. Why? Because infiltration means aquifer recharge. On the other hand, you have to think that basically, if you look at the natural environment, it's the result of an equilibrium that went through evolution. Okay, so if you look at the natural environment in terms of water distribution, rivers, groundwater, as I said, is the result of an evolution. And we cannot, strictly speaking, call it equilibrium because it's under continuous evolution. On the other hand, it's an evolution that is close to equilibrium. When you intervene on that, you take water from the river and you bring water along the channels, and you have losses. And we say that these losses contribute to recharge. It's not granted that this works really like we guess, like we would like it worked. So, okay, it's increasing recharge, but it's something that has not undergone a long time evolution. It's something that has been there for 30 years, 50 years, a new canal. And how can we say that this is contributing to recharge if we don't study it in detail and if we don't make a long time experiment? So, I mean, it's not a good idea to say, let's take all the water from the river, and if I have water losses, it's not a problem because it remains in the environment. It's not definitely a good idea. The good idea is to try to impact the environment to the least possible extent. And therefore, sometimes I discuss with people about alternative solutions for climate change adaptation, and usually we end up discussing the alternative between reducing losses or building a dam. And you see, it's water demand control, reducing losses, increasing supply, building a dam. And usually people tend to assume that a solution is more effective if it is huge, if it is something that you can see. You see a dam and you say, wow, this is huge. this is really something that must work. If you are told we are reducing the losses, it's not very convincing. So sometimes people tend to prefer the massive solutions. And of course, there are people that are concerned by the environment, but in general, who needs water? Really would like to get a solution. And if the solution is huge, is important, looks important, is more convincing. So sometimes I discuss about this opportunity instead of reducing water losses, and people say, why is that? Because water losses are beneficial to the environment. I wouldn't say that. I mean, the least we impact the environment and the better it is. If we can reach a solution without compromising the environment too much, then I really would say, wow, this is great. Because I mean, it's not just a matter of loving the environment. Of course, we love the environment, but it's not just a matter of that. It's the fact that the environment went through a millennial experiment. I mean, the history of Earth is an experiment that is thousands and millions of years long. If we make another experiment of building a dam and assuming that, I mean, even if then the water goes back to the environment, what is the duration of this experiment? The experience that we have with dams, it's very limited. It's like, 100 years. And how can we really make sure that this is a durable solution, that is something that is going to last for the future generations? I mean, as I said, I would say, wow, if I can get the solution without compromising the environment. And of course, we have also to be aware that we cannot practice all the possible solutions, because one may say, okay, let's build a dam and reduce the water demand. It's not really the solution, because sometimes we don't have enough resources. Solutions cost money, cost resources in general, environmental resources. So how can we reduce the losses? For instance, if we pave the canals with concrete, this is a possible way of reducing losses. If we cover the canals to reduce evaporation, this is a possible solution. And we have also modeling tools that may help us to understand the amount of saving. And then, of course, there are downsides. If you pave a canal, it's not so nice. I mean, it's very nice to see a grass-covered canal. It looks like a natural environment. It looks really nice. If you pave it, it's not as nice. We know that. On the other hand, it's a possible solution, paving the canal. Another possibility is to use pipe flow to bring water to the fields for irrigation. And another possibility is to change the irrigation technique. But this is not reducing losses. Let's talk of this solution later, okay? Reducing losses. How can we, other possibilities? There is relevant research and technical activity on finding the leakages in water supply systems through the use of pipe flow. When you use pipe flow, you have high pressure inside these pipes, and this may cause leakages. Identify them, finding them when you have hundreds of kilometers of pipes. Where is the leakage? It's a problem, because sometimes, okay, you see the pipe is running under the street and you see water flowing in the street from the underground. So you assume that there is a broken pipe. But if the pipe is broken in an open field, how can we find the leakage? If the leakage is important, of course, you see a water flow coming from the underground. But if it is a minimal flow, how can we find it? And there are research activities on the use of acoustic signals, for instance. You study the propagation of the acoustic signal in the pipes, and where you see a perturbation of the signal, we may assume that this is due to a leakage. There is, I mean, a lot of activity, and I don't go into details, but beware that indeed there are also master programs in water resources management focusing on leakage finding. And it's fascinating. I attended last week a lecture given by a technician, and it was really interesting to see how they work. And it's really nice to see the achievements. In some of the cases, they really achieved a lot. Okay, so reducing losses is another possible solution for reducing the water demand. Now, another possible solution, pricing. How to educate people, I said some time ago. If you increase the cost of water, you educate people to save water, and this is a known effective solution. Of course, it's not the final solution, because first of all, you cannot increase the price of water beyond a certain limit. Usually at the national level in countries, there are institutions that are in charge of controlling the water price, and they have the task of making sure that the water price is affordable for everybody, because otherwise it becomes an equity problem. And so we have to make sure that everybody has safe access to water and for the vital needs. And everybody means that even people with reduced resources, with economic problems, they should be granted a safe access to water in any case. So you can't increase pricing beyond a certain limit. On the other hand, we have experience that if we give water for free to people, including ourselves, we tend to, to waste water more than required, of course, we tend to use more water than we strictly require. There are several educational programs that are activated by water boards to educate people to saving water. And then I already mentioned the virtual water trade. Let me see if I have a slide on that. And let me also mention, I don't have a slide on it. Let me mention irrigation techniques, because water for food is it's the real challenge, because water usage for producing food for agriculture is 70% of the total water usage at the global level, more or less the same percentage in Italy. So you understand that we have to care about water for irrigation, water for food, more than water for civil supplies. I give you the percentage in Italy. It's water for food is 70%, 60% in Italy really at the global level, and then we have a 15% of civil use and a 25% of industrial use. These percentages may vary from country to countries, but more or less, as I mentioned, at the global level, we have 2/3 of water that is used for food production. And this is really the challenge, because we have to try to save water there. So reducing the losses in canals, in irrigation systems, it's one possible solution. Another possible solution is to change the irrigation system. And change the irrigation system, optimize it, means that there is a lot of research activity. It means that you don't use any more techniques like let me get a Google page, flood irrigation, which is widely used in Italy. What is flood irrigation? Look at this picture. This is flood irrigation, and the Wikipedia. Let me open it. Okay. This is flood irrigation. It means that you irrigate the field by let the water flowing over it. You understand that here you have high water consumption, at least because you need, at the end of the field, you need some water flowing, still flowing, because flood irrigation is operated by releasing water upstream, and then water flows over the ground by following the direction of of decreasing altitude. But at the end of the field, at the lower level of the field, you need some water still flowing, and this outflow from the field is lost. On the other hand, there is the convincement by several people that for some type of cultivations, flood irrigation is what is needed, okay? And this is residential flood irrigation, okay? And then what is the alternative to that? The alternative is what is called, let's open a Google page, precise irrigation, or let's say let's follow the chronology. First, sprinkler irrigation, and this is a sprinkler irrigation, okay? And let's see here, this is sprinkler. Other examples, this one, sprinkler irrigation. Other examples, let me see something. There are a lot of devices that can be used. There are some huge machineries. Let me see, like this one. You see here on the right, okay? And let 1 second, open image in new tab. Okay, you see this this is a mobile device. Usually these devices can move over wells. You see here there is the wheel, sorry, over wheels. They can move, they are motorized. There is an engine that is moving these devices. They can move circularly, they can rotate around a vertical axis, or they can translate in any direction. So this is sprinkler irrigation. And then finally, let's search in Google precise irrigation. These are very interesting development. So what is precise irrigation? And let's see, let's look at, I think there is a Wikipedia page. Let's see. You see how many links you get: precise irrigation method and their management, and then precise irrigation systems. Cordis, it's a service of the European Union, a smarter, more precise irrigation system, and artificial intelligence and precise irrigation. This is a project of the University of Bologna. And so what is precise irrigation? Basically, let me see the figures. There is no Wikipedia page apparently, but let's see the images. So precise irrigation, here you see also many pictures of sprinkler irrigation, but let me just, okay, this is, for instance, this is open image in new tab. This is an example, I am magnifying it. So what does it mean, precise irrigation? It means that you deliver directly to the plant, to each plant, the exact amount of water that the plant needs, drop by drop, okay? And this is another example, you see, managed with a phone app. And I think it is interesting, let me check. Using drones. And this is meteorological system, because they monitor rainfall, and then by knowing rainfall, temperature, the type of crop, they compute through agricultural models, they compute the amount of water that is required, and the precise irrigation distributes directly to the plant. I don't see here, you see, for example, here, let's see, okay, now it's good quality. Open image in new tab. Solar panels that are ensuring that the meteorological station works, and also the energy may be used in order to pump the water into the pipes, because precise irrigation is a pipe irrigation, and then you need some pressure, you need to put the water under pressure, you need some energy, but the energy can be generated through small solar panels. And other examples, let me see. Yeah, this is what I wanted. You see drop by drop here on the right, where you see my mouse, drop by drop directly to the plant. Or let's see here. These are really interesting development. If you're interested, there is an experimental field close to Bologna here. You can look for Aqua Campus, where they test several irrigation techniques, precise irrigation techniques. And I went there several times to bring students there. They are testing several methods. And you see here, let me see, Aqua Campus. Visit. Okay. They in their website, they describe all the techniques. I'm not sure if there is the English version. I think so, but I can't find it. Anyway, there are several figures, interesting images. And if you're interested in this, in maybe also in delivering a presentation and to your colleagues, there is a lot of information that can be found. Okay, let me close this. Let me go back to the PowerPoint. There is another possible solution for saving water beyond changing the irrigation techniques. This is delicate. It is normally delicate because people are not willing to accept it. And it's changing the model of agricultural production, changing the crop, in a few words. So there is today, after globalization, there is the trend. There is a trend that has been activated of producing the food, producing the agricultural production, selecting the crops, basing on the market requirements, the market dynamics. So I give you an example. In the region here around Bologna, 20 years ago, more or less 25 years ago, they started producing kiwis, because kiwis was a very profitable production. But kiwis require a lot of water, and therefore they had to build a lot of small artificial reservoirs in order to give water to the kiwis. And this is something that has impacted water resources management in this region significantly. So basically, there was this trend in following the market, and with globalization and the increase of export of agricultural production, this has introduced several changes, several impacts on water resources management. Now, you know that after the economic crisis of 2007-8, and after the international tensions, after the pandemics, the export has been reduced. So if you look at the data of export of for Italy of agricultural production, there is a clear downtrend and downward trend. And so now the question is it the right time to think at a different model that doesn't follow the market in developing agricultural production, but rather follows the needs of ensuring sustainable water resources management? There is a presentation on my website. Let me go on my website, which you may be interested to see. And it's somewhere here. And you have to look at the research column and go down, and it's pandemics, geopolitics, economic inflation, and water resources management. So if you're interested, this presentation provides some more details. It's an easy reading on the connections between economy and international trading, international politics, geopolitics, and agricultural production. And basically, this presentation highlights that this can be the right time to identify a different model. And changing the crop is potentially able to reduce the water demands a lot. The logic should be that crops that are really water demanding should be cultivated where water is available and not where water is not. And of course, it looks like a stupid statement, but actually what happens frequently is that, you know, when the market promotes some types of production, people tend to follow the market, and it's of course obvious. And when I talk to farmers, they don't want to listen to any other argument other than the market, because it's their, I mean, it's their salary. So it is delicate, but it is also very interesting, because any delicate, I mean, solution is very interesting. Okay, now, do you have any questions so far? Before I have a couple of slides still to present to you. So I can breathe a little bit, because, you know, talking in front of the screen is, I'm not sure if you realize it, but when you talk in front of an audience, it's slower lecturing, which is on the one hand nice, because it's less demanding in terms of energy for the speaker. And it's also nice because the students can follow better. On the other hand, of course, it's less efficient, you know. In any case, the moral of the story is that when I talk in front of the screen, I become more tired. Be patient. Okay, now, another possibility, reducing the impact of extremes. This is another possible solution to save water. It is not immediately understandable. One may think something like, but what's the matter here? If I reduce the impact of floods, I don't really get a direct gain in water resources management. Actually, I mean, if we reduce the impact of extremes, the potential gain is very relevant. Think of droughts. Droughts are an extreme, so reducing the impact of drought, of course, has a relevant effect on water resources management. And also, if you think of floods, because floods generate an impact on water supply system, on irrigation system, and an impact on agriculture. And to recover from floods, very often we need more water, because we have to clean everything. We have to clean the canals, we have to clean the water supply system, we have to clean the houses, and the water demand increases. So, of course, in the aftermath of a flood, you have a lot of water available usually, but sometimes it is very short, the time between the flood and water scarcity. Especially in small basins, you may pass from a flood to water scarcity in few hours. So reducing the impact of extremes is indeed important. And for instance, think of insurances for farmers, because a farmer may be concerned by the onset of a drought, because the drought may cause the loss of the production. So if the farmer is concerned by the possible onset of a drought, the farmer tends to use more water at least to ask for more water in order to have the possibility to use it just in case. And another possible solution, because I mean, more water costs money also to the farmers. Another possible solution is to activate an insurance. So an insurance over droughts and an insurance over floods. This is a solution that is increasingly applied. Insurance companies are extremely interested in climate change adaptation, and they hire people, experts in statistical analysis, in probability, in decision theory, because they want to know